Okay, so we're going to prove this result that if we have distinct positive integers m and n, then this sum m over n plus n over m can never be an integer. So we need m and n to be distinct first of all, because if they were the same then we just have 1 plus 1, which would be an integer. And we need them to be positive because, for example, you could have 2 over negative 2 and negative 2 over 2 would also give us an integer. But then if we have m and n are distinct positive integers, it'll turn out that this can never be an integer. So we're going to follow a proof by contradiction. So we can start by assuming the opposite is true. So we can assume that this is an integer. So let's write this out. We'll let m and n be distinct positive integers. And we're also going to say that m over n plus n over m is an integer. We'll say that this is equal to some integer k. And this is going to be positive because m and n are both positive. So the next thing we'll do is let's imagine we just simplify these two fractions if we need to. So if m and n have any common factors, we'll just simplify this and we'll write it as a over b plus b over a. And you'll see this is still equal to the same value k because we haven't changed the values of the fractions, we've just simplified there. So let's just write this out as well. We've got that a and b are, we say they're co-prime, they don't have any common factors, so they have no, we can say they have no common prime factors. But they will still have the common factor of 1, because they're both integers. So a and b have got no common prime factors now, and then we're going to work with this to try and get a contradiction to our original result, which will show then that this can't be possible. So starting with this equation, if you imagine just multiplying by a and b on both sides, we get, first of all, this fraction becomes a squared, b over a becomes b squared, and the right-hand side becomes k times a times b. And then if we take everything over onto the right-hand side, we get kab minus b squared is now equal to a squared. And then we can even factorise on the right-hand side, we get b times ka minus b. And this is equal to a squared. So we're now going to think about the left-hand side here. You can see is a multiple of a, which means that the right-hand side is also going to have to be a multiple of a. But just to think about this really deeply, we can think about the prime factorisation of a. So if you imagine we write the prime factorisation as p1 times p2 up to pr, and the only difficulty here is maybe if a is equal to 1, then it doesn't have a prime factorisation like this. So we'll come to this separate case in a moment. So if a is written like this, where we've potentially got some repeats, like p2 could be equal to p3, for example, then we can write the prime factorisation of a squared as p1 squared, p2 squared, all the way up to pr squared. And we'll just add a note here that maybe it's different if a is equal to 1. So why have we done this? Well, if you think about the prime factors of a and the prime factors of a squared, certainly all of the prime factors of a have to belong to the left-hand side here. We can say that this is a multiple of a. So we can write this with this notation. You just read this as a divides a squared. But then, of course, if a is a multiple of a squared is a multiple of a, then we can also say that the right-hand side has to be a multiple of a too, because these are equal. So we can just write underneath then that a divides b times ka minus b. And now for this step, we've got that a divides b times ka minus b. So this is why we've got the prime factorisation here, because you think all of the prime factors of a have to somewhere belong to this product, b times ka minus b. But of course we know that a and b don't have any common prime factors, so actually all of a's prime factors must just be in this ka minus b then. So we can just say that a divides ka minus b. So this is really interesting now, because we're saying that ka minus b has to be a multiple of a. So we can write this, let's say it's a multiple of a, so we could call it c times a perhaps, and this is equal to ka minus b, where c is some integer. So we can do a bit of rearranging here. We can take b over onto the left-hand side, subtract c times a. So then we get b is equal to ka minus ca, so we can factorise this as k minus c times a. But now we can see with this expression that, well, b has to be a multiple of a then, because it's some number multiplied by a. And this is a problem, because if we want b to be a multiple of a, we've already said that actually a and b don't have any common prime factors. So the only possibility here is, if you think, for example, if a was 2, then b would have to be a multiple of 2, and they would have a common prime factor of 2. Or similarly, if a was 3, then b would have to be a multiple of 3. If a was 4, b would have to be a multiple of 4. So the only remaining possibility is actually this weird special case where a is equal to 1. So we can conclude so far then that, following this line of argument, that a actually has to be equal to 1 if a and b don't have any common prime factors, but b is still a multiple of a. So now that we've got that a is 1, we'll clear some space here, and then we'll see if we can get this to lead us to a contradiction, which would then show that m over n plus n over m can't be an integer, like we assumed at the start. And now we can use the fact that a is equal to 1, remembering that we've got a over b plus b over a is equal to this integer k. We can just substitute in a as 1, and then we get that 1 over b plus b over 1 is just b, has got to be equal to this integer k. And now we know that b and k are both integers, so in order for this to all be equal, we'd also need 1 over b to be an integer for this plus b to give us an integer k. And the only way for 1 over b to be an integer is actually when b is equal to 1. Because if we had, for example, b was 2 or b is 3, we'd have a half or a third. The only way to get 1 over something to be an integer is for b to be 1 itself. So we've got that b is 1, and we've also got that a is 1. But this is a big problem now for our fraction a over b, which is supposed to be equivalent to this fraction m over n. So we've got m over n is equal to a over b, and this is just 1 over 1, so this is just equal to 1. But then this implies that m is actually equal to n, and this is where we get our contradiction now, because we're supposed to be working in this case where m and n aren't equal to each other, and then we assume for a contradiction that m over n plus n over m is an integer, and we follow this sequence of steps, and then this implies that m is equal to n. So this is actually our contradiction then, and the proof is complete, so we can conclude that it's not actually possible to have m over n plus n over m be equal to an integer in this case, where m and n are distinct positive integers.